So what formulas do you have for entropy so far?
There's a formula for when temperature is constant, and then, sorry, I'm still getting familiar with the material. So then it'd be delta S over work over temperature equals work over temperature, or sorry, not work, heat.
Yeah.
Q over T.
Divided by temperature, if temperature is constant. And if the temperature is changing, but not a whole lot, if the temperature is just changing a little bit, you can still use this formula. You would just need to use average temperature. And then you get an approximation, but it's a pretty close approximation. And that average temperature there is literally just the average of the initial temperature and final temperature. If temperature doesn't change much. And that's kind of relative. Like if the temperature is only changing a few degrees, you can definitely use this. If the temperature is changing like 20 or 30 degrees, this is still pretty close to accurate. If the temperature is changing by a few hundred degrees, it wouldn't be a good idea. But if the temperature is changing drastically, what formula will tell you the exact delta entropy?
Delta S equals heat capacity, and then ln of T final over T initial, I think.
Yeah, that should give you the exact delta S, not just an approximation, if the temperature is changing.
And heat capacity is mass times specific heat?
Yeah.
Okay.
Or you could use number of moles times molar specific heat. And that's specifically the constant volume molar specific heat, because we're only looking at heat, we're not caring about work. So let's try an example of this. Let's say we have a block of ice that we're trying to melt. Let's say we have a block of 5 kilograms of ice at, let's say, negative 20 degrees Celsius. And let's say we want to, bring this up to a boil. Let's say we want to boil the whole thing. And we want to figure out how much entropy that's going to, how much change in entropy that's going to involve. First of all, without even doing any calculations, would you expect this to involve entropy increasing or decreasing?
Increasing.
Yeah, and why is that?
I'm just thinking of like the 3-phase diagram, and as you move from like solid, liquid to gas, that like the only thing about it is like in gas, the particles are moving quicker and like more fast, so it's more disordered, so there's more entropy compared to a solid where it's more uniform.
Mostly yes, although a couple of cautions I have with that. First of all, a gas doesn't necessarily mean the particles are moving faster. The speed at which the particle is moving is really more about temperature. So if you have, for instance, let's say liquid water at 100 degrees Celsius versus gaseous water also at 100 degrees Celsius, the liquid molecules and gaseous molecules would be moving at the same speed on average. If it's a higher temperature, then they'd be moving faster. But just the transition from liquid to gas doesn't change the average speed. What it does do, however, when you're going from, let's say, solid to liquid or liquid to gas, what's happening to the molecular bonds?
They're breaking.
Right, you're breaking bonds, which means ultimately you're allowing more freedom of movement. You're changing molecules which are rigidly wiggling in place to molecules which are free to move around. And by allowing more freedom of motion, you're increasing the number of possible microstates. So breaking bonds directly means you are increasing freedom of motion and therefore increasing omega, the number of microstates. And if we go back to the original definition of entropy, that entropy is Boltzmann's constant times logarithm of the number of microstates. Anytime you increase freedom of motion, anytime you make the particles more free to move around, that's an increase in entropy, because you're allowing them to exist in more possibilities. There are more possible ways for the atoms to be arranged. And more importantly, more ways for the energy to be arranged amongst the atoms.
I have a question. Are modes the same as microstates?
Not exactly. Modes are ways that the particles can have energy. Microstates are the number of ways energy can be distributed, or the number of ways the molecules and energy can be arranged. So for instance, let's say a diatomic molecule as a gas could have, let's say, 5 microstates. Sorry, 5 modes. Diatomic gas, let's say H2, has 5 modes. That means there are 5 ways that it can have energy. It can have translational kinetic energy in 3 dimensions, could be rotating around 2 different axes. But that doesn't mean it has 5 microstates. There's probably going to be way more microstates, because microstates are about how much energy can go, or how many ways energy can be distributed to those modes. For instance, a microstate might be there's a certain amount of energy in the x direction translational energy, translational kinetic energy, a certain amount of energy in the y direction translational kinetic energy, a certain amount of energy in spinning around the z-axis. So a microstate would be listing out how much energy is in each of those modes. So the number of microstates is going to be more than 5.
I see. Thank you.
Mm-hmm. And then more broadly, the total number of microstates is the total number of ways energy can be distributed amongst all the modes of all the molecules in the system. So number of microstates is going to be a colossally huge number. And this is one reason why we define entropy in terms of a logarithm, because omega is colossally huge. Logarithm of that number is going to be a smaller, more manageable number. And also multiplying by Boltzmann's constant, which is very small, shrinks it to an even more manageable size. Any other questions on that so far? I also want to mention that it can be kind of dangerous. I don't know if dangerous is really the right word, but not always accurate to think of entropy as meaning disorder. Entropy classically is usually thought of as being kind of synonymous with disorder, but formally entropy is all about number of microstates. Entropy is an actual number. It's the number, well, logarithm of the number of microstates, the number of ways it can be arranged. So when we say entropy is increasing, we really just mean there's now more ways that the system could exist than there were before. Whereas disorder is kind of a more subjective thing. Like somebody might look at a system and say this is very disorderly, and somebody else might look at the same system and say it's not very disorderly at all. But entropy is an actual specific quantity. You can actually assign a number to entropy, and that's the entropy. So it is often the case intuitively that systems that we tend to think of as disorderly are usually higher entropy systems, but don't rely on that because it's not always reliable, not always accurate. Entropy literally means number of microstates modified by the logarithm and the multiplier. We can also look at this in terms of if you want to change ice to steam, do you have to add heat or remove heat?
Add.
Yeah, this is all about adding heat in this case. And if you take a look at these formulas for delta S, these both suggest that if you're adding heat, you're increasing the entropy, because if heat is positive, then delta S will also be a positive change. And likewise here, if you're increasing the temperature, higher final temperature divided by lower initial temperature is going to be a number greater than 1, and logarithm of a number greater than 1 is going to be a positive result, also suggesting entropy increases. So all of these ideas, the idea of breaking bonds to increase freedom of motion, the idea of adding heat to the system, the idea of raising the temperature, all of those suggest an increase in entropy. Any questions on the conceptual side of that so far? So let's try running the actual calculations. If we want to know exactly how much the entropy increases, which formula could we use here?
The heat capacity times the logarithm, or the natural log of TF over TI.
Because we're going from -20 to +100. And of course, we'll have to convert those both to Kelvin. There's one slight problem though. What heat capacity would we actually use?
I was working on a problem earlier. Sorry. And I was confused because would you have to do it in 2 steps? Since you would have like the heat capacity at solid liquid.
Yeah, because the thing is solid ice and liquid water have different specific heats. They have different properties. So we're going to have to split this up into the portion, the changes while it's in the process of warming up as a solid and the process while it's warming up as a liquid. And also the phase changes itself, or the phase changes themselves. We need to take those into account as well. Because a phase change involves adding lots of heat, even though the temperature is not changing. So for the phase changes, we're going to want to use the Q over T formula because we're adding heat at a constant temperature. In other words, we should really split this up into several sub-processes. The first thing you do is if you add heat to this cold ice, it's going to start warming up. In fact, it can be very useful to look at this on the 3-phase diagram as well.
Can I ask a question really quick? Just clarifying. For temperature is constant, you would use that equation when there's a phase change?
Q over T?
Yeah.
Yeah.
Okay.
Yeah, Q over T or even Q over T average if the temperature is just changing a little bit. And this is especially useful for phase changes because a phase change is all about adding heat while the temperature is not changing.
Okay.
So if we take a look at the initial case was cold ice. And we're going to warm up the ice to 0. But then the next thing that happens is we're going to melt the ice. So that's a separate process. And then after that, we're going to warm up the liquid water, which is another separate process. And then also we want to boil it. We want it to turn into steam. So we're going to go through another process. So we've really got 4 steps here. Warming up the ice, melting the ice, warming up the liquid water, and boiling the liquid water. And then once it's all boiled, we're done because we just need to get to steam at 100. So what we want to do is consider each one of these processes and figure out what's going on there. So for instance, this first process, warming up the ice. Because we're talking about a temperature change, but it's a fairly small temperature change, only 20 degrees, we should be able to use Q over T average as a pretty good approximation, or we can use heat capacity times logarithm of the temperature ratio to get the exact value. So let's take a look at both of those just to see how they compare. For the exact value, we're going to use heat capacity times logarithm of T final over T initial. And how would we find the heat capacity here?
You would just do the mass that's given 5 kilograms times the specific heat.
Right. So that's just going to be 5 kilograms. And you happen to know the specific heat of solid ice?
I think, I'm not sure.
Like
Yep.
2.05.
What was that?
Isn't it like 2.05 or 2.03, something like that?
Yeah, that sounds about right. Yeah, 2.05. Yeah, 2.05 kilojoules per kilogram Kelvin. So the kilograms cancel out. We're left with 10.25. And the units there will be kilojoules per Kelvin. Got to be careful to keep track of that. Times logarithm of, and then for temperature, what should we use as the final temperature here?
0 degrees.
Right. Of course, that needs to be in Kelvin. So what would that be?
273.
Yeah, 273 Kelvin. And then the initial temperature was -20, which is the same as?
253.
Yeah. everything's in Kelvin, so kelvins and kelvins cancel out when we divide. And then we just need to multiply that out. 10.25 times logarithm of 273 over 253. So I'm getting about positive 0.7798 kilojoules per Kelvin. So that would be the exact delta entropy of this process, the process of warming up the ice from -20 to 0. Any questions on that so far? And while we're at it, let's take a look at the approximation also. We can say delta S is approximately heat over temperature average. The average of 273 and 253 would just be 263, halfway between those. How would we figure out how much heat was added during this process, though?
Could you use delta E thermal?
Yeah, and probably the easiest formula for that would just be the MC delta T from way back at the beginning of the quarter, because we have M times C already. So we can just take M times C times delta T, which is 20 kelvins. So the heat capacity times 20 times plus 20 Kelvin, I'm getting about 205 kilojoules. So that's the amount of heat it takes to warm this up from -20 to 0, divided by that average temperature. And I'm getting about positive 0.7795 kilojoules per Kelvin. So that's an approximation versus the exact value. But note that these are remarkably close. The approximation, even at a plus 20 degrees worth of temperature change, this approximation is off only by 0.0003 kilojoules per Kelvin. So the approximation, the Q over T average, is remarkably accurate for fairly small changes in temperature. If you were changing temperature by a large amount, then this wouldn't work so well. But just a few dozen degrees, it's going to be remarkably close to the exact value. And of course, you also have to be careful not to accidentally apply this if there's phase changes in between. We couldn't just jump straight from -20 to 100 because there's phase changes in between. So we've got to consider those phase changes and the different phases properties as well. But 0.7798 is going to be the closest we can get here. Well, other than writing out more digits from the calculator. Any other questions on that warming up the ice so far? Then let's try out the first phase change when we're going from solid to liquid. From solid to liquid, melting the ice. What formula should we be using for the process of melting the ice?
Delta E bond.
Yeah, because the amount of heat, we're just adding heat to break the bonds, to melt, to change the phase. So heat is delta E bond. We can use our usual delta M, delta H formula for that. And since we're melting all 5 kilograms, delta M is +5. And delta H for water melting, we can look that up on the data table as usual. Water melting 333.5 kilojoules per kilogram. Kilograms cancel out, we're left with kilojoules. That tells us the amount of heat. So 333.5 times 5, 1,667.5. We've got the amount of heat, but how do we use that to find the change in entropy?
Because the temperature is constant, can you divide by 273?
Yeah, heat over temperature should work fine because it's all happening at a constant temperature. So delta entropy is just going to be heat over temperature. And as you said, it's all happening at 273. So we just divide those. And I'm getting about +6.108. kilojoules per Kelvin. So that's the increase in entropy associated with the phase change. And note that that is much larger than the change in entropy associated with just raising the temperature 20 degrees. Phase changes tend to involve very large increases in entropy, partly because it usually takes a lot of heat to do so, but also because more conceptually, breaking bonds allows a lot more freedom of motion. That these molecules are now much more free to move in a liquid than they were in a solid. And once we get to a gas, they will be even more free to move. Any questions on that so far? And then the next process, we're warming up this liquid. So what formula should we use for that?
Heat capacity times the natural log of temperature final over the initial temperature.
Yeah, that'll give us the exact value. And you could also use heat over average temperature. So figure out how much heat it takes to warm up the water and then divide by the average temperature, halfway between 273 and 373. That will be not quite as accurate because we're going up by 100 degrees instead of just 20 degrees. And the larger the change is, the less accurate this becomes. But even for 100 degrees, I would still expect it to be pretty close to accurate. But let's go ahead and use the exact formula. Heat capacity, we can still use mass times specific heat. We're just using specific heat of liquid water. So that's 5 kilograms times liquid water, 4.18 kilojoules per kilogram Kelvin, times logarithm of, and again, we want to have these temperatures in Kelvin. So final 373 divided by initial 273. And Kelvins are going to cancel out anyway. Punch that all into a calculator. And I'm getting about positive 6.523 kilojoules per kilogram, or kilojoules per Kelvin. So a significantly larger amount of change in entropy than the previous one for the ice warming up, partly because we're going through 5 times as much temperature change, but also water, liquid water has a higher heat, that higher specific heat than solid ice does. So it takes more heat per degree, more heat per Kelvin. And lastly, we also want to change the phase from liquid to gas. So what formula would we have to use for that?
Just heat divided by temperature.
Yeah, during the phase change, the temperature is constant, so we can just use heat divided by temperature. Heat, once again, is just going to be delta E bond, so we can still just multiply the mass times the latent heat. Mass, 5 kilograms. And then the heat of boiling for water vaporizing. Water, heat of boiling, heat of vaporization, 2257 kilojoules per kilogram Kelvin, divided by, or kilojoules per kilogram, divided by the temperature, 373 Kelvin. So that should tell us how much entropy is in, how much change in entropy is involved with the boiling process. So that's about 30.3 kilojoules per Kelvin. So we've got all these changes in entropy. And then what if we wanted to find the total change in entropy for the entire process?
And you could just add them all up.
Yeah, entropy changes are additive. We can just add these changes together to find the total change in entropy from start to finish.
Just a question about the units of entropy. So it's just energy per Kelvin.
Yeah, joules per Kelvin or kilojoules per Kelvin, whatever you're measuring energy in, divided by kelvins.
Okay, thank you.
Mm-hmm. And that's partly because of, I mean, if we're calculating it as heat over temperature, that naturally becomes joules or kilojoules per Kelvin. Also, heat capacity is measured in kilojoules per Kelvin or joules per Kelvin. And if you even go back to the original definition, Boltzmann's constant times logarithm of number of microstates, Boltzmann's constant is also measured in joules per Kelvin. Any other questions on that? And then we can also graph this process. Have you seen the temperature versus entropy graphs?
Yes, I was just going to ask if you could actually go over those and just the calculations you could derive from them.
Yeah, and I think this would be a good example of that, because the temperature versus entropy graph is another state diagram, very much like the pressure volume graph, just describing the state of a system, maybe initial state, final state, and the process it goes through. And we can do exactly that with temperature and entropy as the axes instead of pressure and volume as the axes. So the TS diagram is a graph that I think it typically has entropy on the horizontal axis and temperature on the vertical axis. Is that right? Entropy. Yeah, that should work. So we typically draw entropy on the horizontal axis, temperature on the vertical axis. And each one of these points, like the initial state where we had ice at -20, and then later we had ice at 0, each of those instants in time, each of those states of the system could be graphed as a point on this diagram. And then each process is going to be a path, maybe a straight line, maybe a curve. So let's mark some of these data points. The important temperatures here are going to be -20, 0, and 100. Or in Kelvin, 253, 273, and 373. And we start off at some low temperature, low entropy. And we usually don't really care what the value of entropy is. All we really care about is how much it's changing, because all of these formulas we're working with are delta entropy. So we're going to have some low initial entropy, S initial. And we know we start off with ice at -20 at that low entropy. And then we're going to change, since we're raising the temperature, but also increasing the entropy by about 0.78. That's an increase in entropy and an increase in temperature.
How did you get the first point right there for initial entropy?
Because at the very beginning, before we added any heat to the ice, we started off at 270 or 253, because it's -20°C. 253 Kelvin is the temperature, and just some arbitrary low value of entropy at the beginning. So we don't really have a number for initial entropy, but we don't care about how much entropy it has. We just care how much the entropy is changing during this process. So we're going to mark these as just initial entropy, and then initial entropy plus some amount, initial entropy plus some other amount. For instance, during the warming up the ice process, we're just increasing the entropy by, let's say about, I'm just going to round this off to about 0.8. So we increase the entropy by about 0.8. To get the new entropy. And we're going to transition from initial entropy and temperature 253 to this new higher entropy and 273. So that's the initial state, and then the final state after we've finished warming up the ice to the 273. And then in between, we're going to have a path linking one to the other. And the shape of that path, much like the pressure volume graph, the shape of that path is all about how much of it is heat versus how much of it is work. And in this case, what are we assuming about heat versus work?
Are we assuming that it's all heat?
Yeah, in this case, we're assuming we're just adding heat and there's no work done at all. So that's going to be a specific shape of path. And it's going to be, if I remember correctly, it's not a straight line. I think it's curving lower than a straight line would. So something like this. For short distances, you can treat it as almost like a straight line. But then the next stage of the process, we are now melting the ice. So as we melt the ice, what happens to temperature?
It's constant.
Right, which means we're not increasing or decreasing. We're not going up or down on the graph at all. Temperature stays constant. So you've got the warming up the ice, and then we're going to have the melting the ice process. We can't go up or down because we're not changing the temperature, but we are increasing the entropy by 6.1. So that's going to be going to the right. Melting the ice. So melting the ice is just going to be going straight to the right on the graph. And that's going to correspond to a new entropy that is what we had before plus an extra 6.1. And I'm rounding off a little bit here. Let's just call this about 6.1. So we added 0.8. We added an extra 6.1. We're now at 6.9 above the original. S initial plus 6.9. And then we just keep adding more and more as we go along. So that would be a process involving no temperature change at all. In fact, that's in terms of the pressure volume graph terminology we've been using. What do we call a process that involves no change in temperature? If the temperature is constant, what do we call that process?
A phase change?
In this case, it happens to be a phase change, but more generally in the pressure volume graph, what's the terminology we use?
The adiabatic process?
Close, although adiabatic doesn't mean no change in temperature at all. Adiabatic means no heat transfer.
Isothermal.
Isothermal, exactly. Iso meaning same, thermal meaning having to do with temperature. So a horizontal line on a temperature entropy graph represents an isothermal process because there's no change in temperature, so you're not going up or down at all. And this is an interesting contrast because on a pressure volume graph, an isothermal process is going to be this weird curve, not a straight line. So this is a very, very different sort of process here. Like in the case of warming it up, we were adding no work. What does a pressure volume graph look like if there's no work involved?
It's a vertical line.
Right. So a path involving no work would be a vertical line on a pressure volume graph, but a weird curve on a temperature entropy graph. An isothermal process, no temperature change, is a weird curve on a pressure volume graph, but is a nice, neat horizontal line on a temperature entropy graph. So there are some processes that look much tidier and easier to deal with on a pressure volume graph, and other processes that look much tidier and easier to deal with on a temperature entropy graph.
So the no work process, can you call that isochoric?
Yes, that would be isochoric because no work implies no volume change. Although since we're talking about solids and liquids, that's not really as applicable. Usually for isochoric and isobaric, we're specifically talking about gases. Because for solids and liquids, we usually don't expect the volume to change anyway. But yeah, I guess we could technically call that isochoric. It's just that that's kind of the default when we're talking about solids and liquids. And then the next process, we are warming up the liquid. That's going to be another process involving temperature increasing as entropy increases. And we know that entropy is increasing by 6.5. So we take the S initial plus 6.9 we already have, add an extra 6.5 to that, and we get 13.4 above the original. I'm going to need some more space here. So we add 0.8, we add an extra 6.1, we add an extra 6.5 beyond that. And also in this process of doing so, we're raising the temperature all the way up to 373. So we're going to end up somewhere around here. And because that's also an isochoric process, we're allowing the temperature to change, but we're not doing any work. That's going to be another curve, something like that, I believe. So this would be the process of warming the liquid. Warming the liquid up to 373. And then after that, what do we do with that liquid at 373?
You undergo a phase change.
Right, and that phase change,
temperature constant.
Exactly, temperature is constant during that phase change, so that's just going to be a horizontal line. And also that involves a very large increase in entropy, 30.3, so that's going to be much larger. This is not exactly to scale, but here's the boiling process. Boiling the water. All the way out to what we had before plus an extra 30.3. So that'd be S initial plus 13.4 plus an extra 30.3, so that's 33.7 above the original. So this would be the temperature entropy graph for the whole process, from cold ice to steam. Any questions on that so far? And also, if we take a look at the area under the graph here, because for the pressure volume graph, area under the curve was pretty important. For the temperature entropy graph, let's focus on just this rectangular portion, because rectangles are going to be easier for area. How would you calculate the area under the curve there?
You could multiply the temperature, since it's constant, times the change in entropy.
Right. Because the height of this rectangle is just the temperature, 373. And the width is not the entropy, but the change in entropy from here to here. So the area is going to be temperature times change in entropy. However, because it's a constant temperature process, what's our formula for delta entropy if the temperature is constant?
Q over T.
So if we multiply T times Q over T, what do we get?
Just Q, because the T will cancel out.
Exactly. So that is actually the area under the curve here. Just like the area under the curve in the pressure volume graph tells you work done, the area under the curve in the temperature entropy graph tells you the amount of heat transferred during that process. And in fact, that turns out to be true even if it's not a simple rectangle. Like if you take a look at this entire region under the curve. The entire region under the curve, from the curve all the way down to the axis, from initial entropy to final entropy, that area tells you the total amount of heat transferred during that process. And in this case, we don't even need a negative sign like we did for the pressure volume graph. For pressure volume graph, area under the curve equals the opposite of work, because of the expanding volume means work is leaving, compressing volume means work is entering. But here, increasing the entropy happens because you're adding heat. Decreasing the entropy would happen because you're removing heat. So in this case, the sign on heat is the same as the sign on change in entropy. So we can just say heat is the integral of T integrated with respect to S, from S initial to S final. Or more geometrically, the area under the curve. But this is why it's often very convenient to have both a pressure volume graph and a temperature entropy graph of a process. Both graphs together really give you a much more complete picture than any one individually. Because if you have both the pressure volume graph and the temperature entropy graph, you can immediately find the work and heat just by looking at the area under each curve. And also, like I said earlier, there are some processes that form nice, neat straight lines on the temperature entropy graph, and other processes that form nice, neat straight lines on the pressure volume graph. So it's useful to have both. Any other questions on that?
What would an isobaric process look like on a TS diagram?
Isobaric. That forms a nice, neat straight line on the pressure volume graph, which makes me think it's going to form a messy curve on the temperature entropy graph. It's generally one or the other. The nice, neat straight lines on one graph form weird curves on the other graph.
Okay.
But if you're keeping the pressure constant, then keeping the pressure constant, I think we saw earlier, means you have to add more heat to get the same change in temperature. So isobaric suggests that you're going to need to have this curve bulge out to enclose more area.
I see. So it'd be like a mirror of the isochoric.
I don't know if it would actually be curving like concave down like that, but it would at least be like higher up.
Okay.
It would still presumably have the same initial and final points, because initial and final points depend only on the state of the system, not on the process used. But if you're going from here to here with an isobaric process instead, I would expect it to at least be a curve that's higher up. So maybe less concave, for instance.
Okay. Okay. Thank you.
I'd have to do the calculations to find the exact curve there, but I just intuitively, I know it's going to involve more heat, because you have to apply, if you're holding pressure constant but allowing the volume to change, you need to apply more heat to get the same temperature change, because you're allowing work to leave the system as well.
Is that connected to the fact that the C at a constant pressure is greater than the C at a constant volume?
Yeah, that's exactly why. Okay. Because
cool.
the reason that C value is larger at constant pressure is because it takes more heat to get the same temperature change. And that's because if you're allowing the volume to change, you're allowing work to leave the system.
Okay, that makes sense. Thank you.
Mm-hmm. The other curve that looks nice and neat on the temperature entropy graph is a vertical line, because we saw that a horizontal line means the temperature is not changing. So on a temperature entropy graph, horizontal is isothermal. What about a vertical line? Let's say you're just going straight up. In that case, if you're just going straight up, what's not changing?
The heat.
Right, that would be no heat added, in part because there's no area under that curve. Also, going straight up means you're not going left or right, which means the entropy is not changing. And the way to change entropy is adding or removing heat. So no left or right motion means no change in entropy, which means you're not adding or removing any heat. You are presumably changing the temperature, so you're increasing the internal energy. How do you increase the internal energy without adding any heat?
You increase the work?
Yeah, you're doing work to the system instead. So a vertical line would represent you're doing work to increase or decrease the temperature, but you're not applying any heat. So we would call that an adiabatic process. And again, that's an example of a curve, of a process that looks like a weird curve on the pressure volume graph, but is a nice, neat straight line on the temperature entropy graph. So temperature entropy graphs make it very easy to work with isothermal process and adiabatic process. Pressure volume graph makes it very easy to deal with isobaric and isochoric process because of what's being held constant. Any other questions on that? Or any other questions before we go?
Thank you.
You're welcome. See you next time.
This was super helpful.
Glad I could help. See you next time.